Work energy theorem. The work energy theorem is a fundamental principle in physics that establishes a relationship between the work done on an object and its resulting change in energy. This theorem is particularly applicable in the context of mechanical systems. Here's an explanation in 40 lines. 1. Introduction. The work energy theorem states that the work done on an object is equal to the change in its kinetic energy. 2. Work done. Work, denoted by W, is the product of force applied on an object and the displacement of the object in the direction of the force. 3. Kinetic energy. Kinetic energy, Ki, is the energy possessed by an object due to its motion and is given by the formula Ki equals 1/2 mv squared, where m is the mass and v is the velocity. 4. Mathematical formulation. The work minus energy theorem can be expressed as W equals delta Ki, where delta K is the change in kinetic energy. 5. Positive and negative work. Positive work increases kinetic energy, while negative work decreases it. No work is done if the force and displacement are perpendicular. 6. Conservative forces. For conservative forces, for example, gravity, work done depends only on the initial and final positions, not on the path taken. 7. Example, lifting an object. Lifting an object against gravity involves positive work, increasing its potential energy and, consequently, its kinetic energy. 8. Potential energy. The work energy theorem extends to potential energy, where work done against conservative forces increases potential energy. 9. Non-conservative forces. Non-conservative forces, for example, friction, can do work, converting mechanical energy into other forms like heat. 10. Conservation of energy. The work energy theorem is consistent with the principle of conservation of energy, stating that the total energy of an isolated system remains constant. 11. Applications. This theorem is widely applied in various fields, including mechanics, engineering, and understanding the motion of celestial bodies. 12. Roller coaster example. Analyzing a roller coaster's motion involves considering work done against gravity and friction, explaining the coaster's speed changes. 13. Relation to Newton's laws. The work energy theorem is complementary to Newton's laws, providing an alternative perspective on analyzing motion. 14. Elastic potential energy. In systems with springs, work done compressing or stretching the spring is stored as elastic potential energy. 15. Limitations. The theorem assumes no energy losses to non-conservative forces like air resistance, which might not hold in real-world scenarios. 16. Quantitative analysis. Calculating work done and kinetic energy changes enables predicting the behavior of